Okay, so I'll try to recap that very quickly, and I just realized I made a mistake anyway. Um, so recreating. Oh, no, Megan or okay. Recreating the example from last time, which I forgot to give a name of it last time. Runge's example um, of approximating 1 over 1 plus x squared with two different polynomials. The first polynomial, we interpolate f of x at equally spaced points from -5 to 5. So that's this vector x, just the integers in that range. And I just plug that into f to get the y. And then so P1 is that interpolating polynomial, which we saw last time failed very badly to approximate f well on the whole interval. And then what I was supposed to do next was the Chebyshev points. Now these are the correct roots of the 11th degree Chebyshev polynomial, and I need 11 points because I want a degree 10 polynomial in both cases. And then I plug it into f and then get that interpolating polynomial using polyfit. But I just realized I messed up because these roots, these Chebyshev points, they're root of a, these are all fall within the interval -1 to 1 because it's they're cosines of various values. But that's not what I want here. I want points distributed from -5 to 5. So I need to bring that statement back and just multiply these by 5. So these are, at least I remember my diary, scaled to, I should say, Chebyshev points map to the interval -5 to 5. Then plug them into f, get my coefficients of my polynomial. So all of these commands were done last time. But what I did last time was I made separate plots. I plotted the one of equally spaced points way back at the beginning of class, and then toward the end did that for Chebyshev. But I want to feature both of them on the same plot, same figure window. This is a feature I often use when preparing papers involving figures, and you might like to do the same. Subplot lets you define an m by n matrix of sets of axes, so an m by n matrix of plots within the figure window. So I want to have two plots side by side. So that would be a 1 by 2 matrix of plots. And the third argument that's labeled as P here by MATLAB is you select which one you want to work on first. So they're numbered sequentially, like going across the rows. So I would pick either 1 or 2. So I'm going to pick 1. And what will happen is you'll see a figure window pop up. Unless I had one open already. Okay, there it is. Okay, so what it's done here is it's divided the figure window in two, and we have this empty set of axes right here. So what I'm going to do here is I'm going to plot, actually I need a vector of x values finely spaced from -5 to 5. I don't really need a parenthesis for this. So for spacing 1/1000th. And then, so now I could do plot x's and then f of x, and now plot that in blue, just so we have the original function. And then, hold on, and then I want to plug the same x values into my interpolating polynomial for one of equally spaced points. And that's P1. And I'll plot that in red. And we saw last time how terrible that was. And I'll also plot the interpolation points. So x, y with black circles. Okay, so that you saw this plot last time. And now I'm just going to recreate one of Chebyshev points in the other window. So for that, what I do is select the second plot, and that's subplot one row, two columns, and then select number 2 as a current plot. And what you'll see is now the second set of axes becomes active, and there's nothing there yet. Now you have to be very careful with this. Always select the same number of rows and columns as you move from one plot to the next. Otherwise, you'll destroy what was already there. So now I'll do a similar thing. I can just cycle back through my command. So I want to plot F in blue. Hold on. And then I want to plot P2. That's with Chebyshev points. And we see that it's a much better fit, but still not great away from x equals 0. And then finally, plotting the interpolation points, xc, yc in black circles. Okay, and I'm going to make this a little bigger so you can stretch that out. And actually, to get a sense of the comparison, notice that for the x values, they're both -5 to 5. But for the y, on the y-axis, it just accommodates whatever's there. So in the left plot, it goes from -1/2 to 2, whereas for the other one, it's -0.2 to 1. So I want to make these the same. So what I'm going to do is I'm going to change the axis limits on the second plot. And that's the one that's still active, because that's what I selected before. So I can just do axis. Actually, just to be sure, I'm going to select it again. I don't want the first plot to be affected. And I'll do axis, and you specify 4 values, minimum x, minimum y. Then, that's wrong. Minimum x, maximum x, so -5 to 5. And then minimum y, maximum y. And I want them to be the same as what's over here. So that'd be -0.5 up to 2. Okay. All right, so now you can see that the blue curves look exactly the same because the axis limits are the same for both. And now you get a better feel for how much more accurate the Chebyshev interpolating polynomial is compared to the equally spaced one. And as we saw last time, the interpolation points are distributed unequally. They're clustered more towards the boundary. Okay, so what I want to discuss, and we will have time in a little bit for homework 2 questions. I know I normally do that first, but just to finish what I was doing last time, I want to get this out of the way. And I also want to show you, here's something I'm doing a little differently that I'll be doing from now on, because since in this setup where we have going over IVN and also needing the screen to do any MATLAB demonstrations, it makes it impractical, and this is what I found in discussions with colleagues who teach in this room, to use a board. So what I want to do as far as, instead of typing mathematical equations here in MATLAB, what I've done is prepared slides. So what I did for this week's classes, so I have everything from Tuesday's class and also today. And what I'll do is I'll post these after class. I haven't posted them yet because I want to allow for a possibility that based on questions that are asked, I might make changes to these. And then I could go ahead and change them right here and update it quickly, knowing that most of what I need is already in here. So what I have, what I'm starting with is whatever's in the textbook for that section, but then trimmed down. I'm cutting out stuff that I'm not covering anyway, making it more reader-friendly, especially for the math, but also the words. So this is what I covered last time. Okay, and like here, this is the error formula that was introduced last time. It has a similar appearance to the Taylor remainder, and then getting into Runge's example, which I've just done, and then I discussed the Chebyshev polynomials last time. So you might find this less straining to read through than what's in the textbook, but still, and focusing on whatever I actually cover here. Okay, and this, so last time I got as far as this, like the essential properties of a Chebyshev polynomials. What is the leading coefficient? Even or odd function, depending on whether k is even or odd. Here are the roots of the each Chebyshev polynomial. These are just a nice formula for them. And a very important property, because the Chebyshev polynomials are defined as a cosine of something, then when x is between -1 and 1, then their values are between -1 and 1. And that really helps for error estimation. And so that's what I did not cover last time, what actually happens with the error formula. So here's what's happening in this case, how we can actually use the error formula for polynomial interpolation, plus the fact that we're dealing with Chebyshev points, to get a bound, an upper bound on the error. So the difference between your, I'm just going to make this a little bigger, or a lot bigger. Whoops. Okay. So the difference between the function you're trying to approximate, f of x, and then your interpolating polynomial, Pn of x. So in this example, f of x is 1 over 1 plus x squared. Pn is our interpolating polynomial of degree 10, so n equals 10. And the x values used are the Chebyshev points, but they're mapped from -1 to 1 to the interval we're actually working with. So here on this slide, I have a general interval AB, but it's an example, it's from -5 to 5. So the first thing that needs to be done is, so I've labeled the various parts of this formula, is here are the Chebyshev points you're starting with. So here I take the roots of a Chebyshev polynomial of degree n plus 1, so in this case 11. So that corresponds to, if I flick back to MATLAB, these cosines. So those are the points on -1 to 1. But then what I need to do is scale them to the interval I'm dealing with. So we divide by 2 because the interval -1 to 1 has width 2. And then I multiply by b minus a, the width of my new interval. So this gives me points distributed between, they're centered around 0. So it's they're between plus and minus b minus a over 2. But then I shift them by the midpoint of AB. So now these points, the Cj, these are Chebyshev points scaled and shifted to the interval AB you're actually working with. All right. So now I use my interpolation error formula. And if I flip back to that, okay, so this is the error formula we're starting with. We have our derivative, n plus first derivative at an unknown point. We have n plus 1 factorial down below. And then we have this, the product of x minus each of your interpolation points. Now keep in mind, in this example, what are the interpolation points? They're the roots of the Chebyshev polynomial. So what I have here is, if I have a product of linear factors, then what happens is, this is a factorization of a polynomial with roots x0, x1, x2 up to xn. So because I've chosen my xj's to be roots of a Chebyshev polynomial, this is the Chebyshev polynomial right here, almost. This is its factorization. So it's just like, for example, if my interpolation points were 1, 2, and 3, then the product x minus 1, x minus 2, x minus 3, that's the polynomial with those roots. So what we have here is the Chebyshev polynomial, except for one thing. If I take these linear factors, however many I have, x minus x0, x minus x1, to x minus xn, if you were to multiply this out, all right, you can actually tell me what the leading coefficient of this product should be. Just the leading coefficient. You wouldn't be able to tell me anything else, really. But so if I take x minus all of these, multiply it out, and I have a coefficient like x to the, I have a term that has x to the n plus 1. what's the leading coefficient? Yeah, it has to be 1. Because you have these x's by themselves, there's no coefficient in front of them. In other words, this is what's called a monic polynomial. A monic polynomial is a polynomial whose leading coefficient is 1. But the Chebyshev polynomials are not monic. And the reason why is we have this 2 here. So as you generate more Chebyshev polynomials, they're as we generate more of them using this recurrence relation, we keep multiplying by 2, and that's why the leading coefficient is 2 to the k minus 1. So in this case, we have a Chebyshev polynomial of degree n plus 1. Therefore, the leading coefficient is 2 to the n. So in other words, this part of the error is actually the Chebyshev polynomial degree n plus 1 divided by 2 to the n. So now we go back down to here. So that's actually what I've done here. I have my Chebyshev polynomial degree n plus 1 divided by 2 to the n. And then I have this factor also, b minus a over 2 raised to the n plus 1. And the reason for that is it's the scaling from minus 1 to 1, a transformation from going from minus 1 to 1 to AB. And the thing is, Chebyshev polynomials are defined in minus 1 to 1. So that's why I have this thing here, t of x. I'm mapping points in AB. So x is in AB. T is in minus 1 to 1. And that's worked out more carefully over here. This is that part of the error that I showed you earlier, x minus each of your interpolation points. And these are in AB. But I can express this difference of points in AB as a difference of points in minus 1 to 1 times this scaling factor, b minus a over 2. So this scaling factor, b minus a over 2, is multiplied by, multiplies in each of these factors. That's why I have n plus 1 factors. That's why I have this raised to the n plus 1 power. So that's how this expression, this part of the error formula, becomes this. So now I can dump all this into my error formula. So this is my error. I need to see how big this can be. Well, it depends on how big this derivative can be. This n plus 1 factorial, all this is a fixed constant. We have a 2 to the n in the denominator. And here's the best part. This Chebyshev polynomial, Tn plus 1, has to be less than or equal to 1 because it's a cosine. So that's why you don't see that in here. So this number down here in the denominator, 2 to the 2n plus 1 and n plus 1 factorial, that's a pretty dang big number, especially as n gets large. It's a very rapidly growing function of n. So that helps keep the error small. So that's why Chebyshev points are an excellent choice for approximating a function f of x on a given interval ab, as long as you scale and shift them appropriately. And that's why we have much less error than in the equally spaced case. And I showed you last time, for the equally spaced case, this part of the error, so I have like x minus a minus 5, x minus a minus 4, and so forth, multiplied all together up to like x minus 3, x minus 4, x minus 5. All those 11 linear factors when it's equally spaced points, I plotted that for you last time. It was got very large near the endpoints of the interval. So it makes a big difference. Okay, so that's what I wanted to cover, finish covering last time. So when you return to, when you get around to homework 3 on chapter 6, section 6.4, so if you want to refer to today's notes, October 5th, so that's what you could do, because I realized what's happening with people being behind the homework. They, in order to refer to things from class, you have to go back a couple weeks. But what you can do is you can look on the schedule or look at the videos and see, oh, here's when I covered that topic, and you might find useful information there from the homework. Okay, now I want to turn my attention to the homework. Okay. So there's one problem in particular I want to bring up. It's a I know there are many problems in this assignment, but okay, computer arithmetic. Okay, yeah, actually, a question was asked about this some time ago in a concept check. This one. On further reflection, I am scratching it from the required part of the assignment and making it bonus in case you already did it. And the reason why, and even though it's a small part of the assignment, I want to do that because what I intend, but don't always successfully accomplish, with the concept check questions is, if you've done the reading, then presumably these should be easy to do. Unfortunately, this question of floating point arithmetic and commutativity was not discussed in the text. It is now, actually, but so sorry about that. I didn't think that through when I put it in there. So yeah, if you've already done it, or if you want to go ahead and do it anyway, then that's a little bit of a bonus for you. Okay, but that's one thing I want to make sure of, is that these questions, in this concept check question, they're not supposed to be a big ordeal if once you've done a reading in that section. Now, I mean, I have the explorations and exercises to be a big ordeal, so I don't, so I don't want the whole assignment to be sadistic. Okay, so that's one thing I wanted to address. Okay. Also, be sure to keep checking the questions page. Just a couple questions from last night I just put up there. So I'm going to keep updating that. Actually, what I think I'll do in the future, well, I'll look at doing it with this assignment also, since we have a lot of questions here. It's either sorted by date. How many do you think would prefer if I sorted them by question rather than by date? Or does it not really matter? Here, but if you look at the question numbers, 2.2.4, 2.2.1, 2.2.16, they're all over the place, because it just depends on where different people are in the assignment. So then if you want to see, suppose you're struggling with a particular one, and you want to see if it's in here, then you have to look through the whole thing. What? Well, yes, that's true. Yeah. So.
And if you leave it like this, we can tell if something new has been added. Like if you check, oh, something was added on the 4th. I haven't checked since then. That must be.
Yeah. Okay. That's also a good point. So. Alrighty. Well, yeah, and certainly I'll make sure that the question numbers are clearly stated. Okay, this particular one was not about a particular problem, but almost all of these are. Okay, so that way, that way, doing find will actually work if you want to do that. Okay, and then once I start getting questions on a new assignment, I'll just put a separator in here so that anything on a particular assignment is always grouped together. Okay, what about homework 2 questions? Surely there are some. Whether you want to ask them or not, it's never matter. But
I have a question.
Yeah.
I had asked on Tuesday about exploration 2.2.6, and then I went back to it. I got confused again.
Okay. Whoops.
When you talk about
Okay.
So you said that it doesn't necessarily have to be 100 pi to be any number.
Oh no, I mean I just made that choice randomly for a problem. I mean, yeah, you still work with 100 pi in the problem. I'm saying there wasn't anything in particular motivating that choice. Yeah, I could have put anything in there. Well, if I had chosen an integer, it probably wouldn't have been all that interesting. Okay. But yeah, really just like working with different mantissas and adjusting the exponent part accordingly, because for a case where the number is not normalized, because if the number was normalized, only one representation would be possible.
Yeah, I was wondering if we would. I know we have to do three representations of it, so I knew we had to normalize it for, I guess, one of them.
Yeah, because the thing is, that's where you can, since this is a decimal system, multiplying by different powers of 10, positive or negative. But one thing to keep in mind is you only have 5 digits. Well, actually, okay. So what that means is, if you allow a leading digit in your mantissa to be 0, then what's going to happen is your mantissas are all going to be different, and it's not just a matter of shifting by powers of 10, because since you only have 5 digits, let's suppose you make some of those leading digits be 0, and then the rest of them would be non-zero digits, then you're going to lose accuracy. So that's what's going to happen in this case. Because 100 pi has infinitely many decimal places, these representations of 100 pi will have different levels of accuracy. So rounding also comes into play. So, for example, if I choose a different number, E. So if P equals 5 decimal system, my mantissa M would be, and I'm rounding, so 2.7183. And that's in the case where I go with a normalized number, leading digit non-zero. But then, not normalized, I could choose for mantissa, like 0 is my leading digit now, which would not be allowed before. And then, but the thing is, in this case of P equals 5, I've used up a digit. I only have 4 digits left. So now that is my mantissa. And then I need to choose the exponent, so that I'm still representing the same value. Okay. Other homework 2 questions.
So does the exponent have to be between negative 20 and 20?
Yes. Yeah, you're still limited to that. Yeah.
Okay.
Oh, you have a question? Okay. You could ask me after class, or okay, that's fine. All right. Any more? Really? I'm going to see a bunch of sparklingly great homework 2s by tomorrow. Because this thing was just so easy. Yes. Yeah. Oh, actually, I want. Yes, but or I guess I could say, what? How about when I wake up on Saturday morning? Okay, we'll go with that. And I really do sleep in. So in other words, if you're working like really, really late on Friday night, I'll allow it. But here's another thing I'll do, because I don't want to hit anyone with 50% deduction unless I'm really, really obligated to. So here, what I will let you do is if you by Friday night, or should I say the wee hours of Saturday morning, if you submit what you have at that point, then I'll just go ahead and accept those without any penalty. And then if there were some that you didn't do and you submit them later, I'll deduct for those, but only those. So that way you can hopefully salvage most of your grade. Okay. All right. So, all right. I guess I'm ruining some people's Friday nights, but well, no, you are. What? Yes. Okay. All right. Is there another question?
Can you go to page 51? So the last example. You said,
Oh, this?
no, the last example in the box.
Oh, this one?
Yeah.
Yeah.
So in the second line it says e equals log base beta x. So why do we have two like signs here? Like is that a modular sign in front of the log?
Oh, no, it's this, the greatest integer function.
Okay, so what does that mean? The sign.
Wait,
The sign that's
this?
that's
Yeah, so basically you can think of it as the rounding down function. Okay, I'm going to magnify this. And now you do know you don't have to do these, right? You don't have to do these.
Yeah.
Okay, just making sure. I mean, yeah, but it can also help if you're understanding. Yeah, because notice it's this little hook here. So, so this is called the floor function. So what you do is whatever real number is put in here, these brackets down here, they say rounded down to the nearest integer. And then that's the floor function. There's a similar ceiling function where you have little marks up here instead, and that rounds up to the nearest integer. Another way that is often described is, I take this log, and then I'm taking the integer part. So then the decimal part, like 0.513, whatever it is thrown away.
Can you go to example 2.2.4?
Yeah.
So you found the exponential by using the formula x
Yep.
equals mantissa times beta to the power exponent, isn't it?
Okay. Yeah, so that's what happened here. I take the log of it to base 2, round down to get 1. Yeah.
But when you use the formula, you actually don't include the mantissa.
I what?
Like when you use the formula, the x equals mantissa times beta to the power exponent.
Yeah.
You actually don't plug in the formula. I mean, you actually don't plug in the number for mantissa to find the exponent. Why is this?
Because what happens is, because the mantissa in a normalized system has to be between 1 and the base. So its log is going to be between 0 and 1. That's the part that gets thrown away when taking the floor function. So you can think of, if I were to take the log, actually, like, this is what I suggested, if you take the log of both sides of this equation, or after taking the absolute value, then what you get is log x is equal to log m plus e, because you're taking the log to that base. E is an integer. So then the rest of the log is log m. So that's why the mantissa, whatever's in the mantissa itself, doesn't play a role in determining the exponent. So here what I've done is I've separated e into product, the magnitude part, just the 2, and then everything else goes into the mantissa. But now I have a mantissa that's equal to this value, and that's between 1 and my base.
How did you get the mantissa in the second part? Can you explain that again?
Well, because once I found my exponent, I take my number and divide it by 2 raised to that exponent. So it's just like, for instance, okay, if we're working in base 10, your number is 135. I take log to base 10 of that, and I get 2 point something. I round down, my exponent is 2. I divide 135 by 10 squared, and I get 1.35. That's the mantissa. Okay. Yeah, so I find out which part of my number goes into the magnitude portion, and then I divide to get rid of it. And then whatever's left over, that's what I have to try to figure out how to express in terms of binary digits down here. Okay. All right. Anything more?
Can you go to page
50? Going backwards. Okay. All right.
So the formula for multiply is a big block, and in the line after the block it says like where each digit dj and j is between 0 to p minus 1
Mhm.
is an integer satisfying. Like again, there's di. So what's di again?
Okay, so for instance, okay, I'll work in decimal, like because I have an example down below. No, actually up above. Where'd it go? Okay, okay, in this decimal example, this minus 1.23, etc. Or actually, just forget the minus. That's the mantissa. So the 1 is D0, 2 is D1, D2, D3, D4, and so on, up to D8.
So the whole block is called di.
Well, the thing is, each DI for particular I is one digit of a mantissa. So your mantissa is basically, it's a string of digits. And then, of course, in binary, it would just be a string of zeros and ones. So really, and that's why to form the to get the actual numerical value of a mantissa, we have to take those digits and multiply them by the appropriate powers of a base. So, for instance, if this was decimal, D1 times 1/10, your 10th digit, and then D2 times 1/100, the 100th digit, and so on, just to actually form that value. And something you do instinctively in decimal, but applies in any base. Yes.
So when you floor, I'm talking about the previous example.
Yeah.
When you floor like a number,
Yeah.
it just automatically goes down.
Yeah. Now, if it's already an integer, it's just that integer.
So if you had like 1.6,
It goes down to 1.
Okay.
Yeah. Yeah. So it's not rounding to nearest; it's rounding downward. Yeah. Yeah. So MATLAB has several rounding functions. There's floor, ceil, short for ceiling, and then round, that rounds to nearest. Okay. Any other?
Is the one number 1 in binary the same as the number 1 in decimal?
Yes, it is. Yeah, in every sense. Yeah, just because, yeah, we're really 1 and 0 would be the only things that would be interpreted the same. Well, that's because once you're in base 2, then you're not allowed to have the other digits. Well, okay. Well, here's one thing to be careful about when you're talking about sequences of digits. For example, this has completely different meanings when you're in binary compared to any other base. Because if I want a numerical value of this, here we have a context that this is in base 2, so we multiply these by the appropriate powers of 2. But if you're in some other base, you multiply by those powers of that base and get something very different.
But if it's just 1.0, then
That means the same thing no matter what. Yeah. The digits to the right of a decimal point, how they're interpreted depends on the base.
and when we do like format text in MATLAB and type digit 1, then why do we get like 3 FF, not 1?
Oh, because the 3ff is the exponent. Because what happens is the bits that are stored in that format, it's not the actual exponent. It's the exponent plus 1023. So the 3ff, well, let's dissect that. Okay, so what you were talking about, so everyone else can see, is that's what you see. I do 3ff. So 3ff, if I were to write that in binary, that would be zeros. Zero's a signed bit, and then number 0, 1, 1, 1, 1, 1, 1, 1, 1, 1. So 3ff. Now, so now we have 10 ones, a string of them, all in binary. 10 ones in binary is equal to, okay, so 2 to the, okay, let's see, for instance, 9 and 9, 2 to the 10th minus 1. Just like, for instance, if you have 9999, 4 nines, that's 10,000 minus 1, or 10 to the 4th minus 1. So, so it's 2 to the 10th minus 1, and that's equal to 1023. So then, that's what's actually stored in here. To get the exponent, you subtract from this, you get an exponent of 0. And then your mantissa is all these zeros. So there's no, but there's also the implied 1 from being normalized. So, so you still have what you expect. Your mantissa is 1, your exponent is 0, your sign bit is 0, but it's not stored that way, just because of the shift applied to the exponent.
Is that the ones complement?
No, it's not the same thing as that. Yeah. Yeah. So you bring even more computer science into the room. Now that I think about it, if I were to take a guess as to what, okay, so if I have, if I do 2 to the minus 1022, well, there, what's stored in the exponent part is 1. So the only way I can get 1 followed by a bunch of zeros would be, okay. So I need a 1 in this digit. So I'd have to have this value be equal to 1 and then zeros everywhere else. So that should be 2 to the 9th, which is 512, minus 1023. So, okay, 2 to the minus 511. Oh, just missed. Whoops. I need the actual value of that. Oh, okay. Sorry, just had to find out what would get me 1 to all zeros. Okay. That's weird. Because I want the exponent, the stored exponent part, to be equal to 0, 0, 1, 0, 0. Oh, oh, it should be 2 to the 8th, not 2 to the 9th. Okay, so 256. There. Okay. So that's how you get 1. It's 2 to the minus 767. Don't worry if you didn't understand what I was doing. It's okay. But I was just satisfying my curiosity there. Although if you do understand it, then you really understand the floating point system. That this 1 followed by 8 zeros, that's 2 to the 8th. So exponent minus 1023 is equal, you want to be equal to 2 to the 8th, which is 256. but 256. So that means if I solve this equation for the exponent, no, actually, that's wrong. It should be plus. Or I should move this to the other side. Exponent of 256 minus 1023, which is equal to minus 767. So that's why it worked. Okay. Any other homework 2 questions?
I have another question.
Yeah.
I think you talked about this, but for exploration 2.2.9.
Uh-huh. Yeah.
Are we, when we put it in MATLAB, we're going to do it in format hex?
Oh, no, don't do format hex. Just enter them as regular numbers. And so the thing is, if a number cannot be represented because it's too large, you'll get infinity. If it's too small, you'll get exactly 0. Okay. So just to give you an idea as to what numbers fall within the representable range. Let's see. And since the u is the smallest number you can add to 1 and still get something greater than 1, so you could try this and try adding it to 1 and see if it gives you back exactly 1 or 1.000000, because then it means there's something there. So that's how you can tell if a number is like what your u is. Yeah. So to give you an example, I'm going to pick numbers that are way out of range to illustrate. So 2 to the 2,000th. Whoops. I need format short for this. Or actually, I'll do format long. That's way too big. I get infinity. 2 to the minus 2,000, you get exactly 0. Whereas something more reasonable, like 2 to the minus 1,000, you get something. So the true smallest number is as a magnitude in between this range. Okay, so that's for the exponent part. As far as unit round off, added to 1, do you get exactly 1? So for instance, if I add 1 plus 2 to the minus 10, actually 2 to the minus 40 for instance, I get something here. So this number is larger than the unit round off or machine precision. Whereas if I add something much too small, like 2 to the minus 100, it's exactly 1. So too large, 2 to the minus 100, too small. It's like a Goldilocks problem. Too large, too small, just right. So the chart gives you an idea of what is just right. It's going to be in that ballpark. I just chose some extreme examples here, just to illustrate the kind of things you could expect to see. For both the exponent and machine precision. All right. Okay, I want to cover something, so, but by all means, hit me with questions after class and tomorrow, and I'll even stay up late tomorrow night. So, well, I would anyway. I basically sleep 4.5 hours a night because I got things to do. So, okay. For polynomial interpolation, throughout, I've been assuming that the x values for your interpolation points, x0 up to xn, are all distinct. Makes sense. But now we're going to consider a case where they're not, which seems kind of ludicrous, but it actually provides a way to specify extra information about the function that you're trying to approximate, because if I have two interpolation points, so xi and xi plus 1, that are initially distinct, but I let them approach one another. So this is xi plus 1 is converging to xi. The corresponding y values, naturally, assuming everything is continuous, which we'll assume, are also converging to each other. But here we have a change in y over a change in x. Well, that's a derivative. So this value is, this ratio is converging, this difference coefficient is converging to the derivative of whatever function you're approximating, basically the derivative of your data at xi. So that tells us what the derivative of our interpolating polynomial is supposed to be. So, so when we now allow our interpolation points to be duplicated, the x values, then the way we account for that is we specify a certain number of derivative values, and that leads to what is called osculatory interpolation. And the reason for the name is the Latin word for kiss, osculare, is to kiss. So you basically have the 2 points coalescing or kissing each other. So, so what happens is, if I have a certain point, xi, and I list it a certain number of times along my x values, so k times, then I have to specify what is the y value, what is the y prime value, y double prime, etc. I'd specify the function value and all its derivatives up to order k minus 1, which makes sense because if I list an x value k times, I should have k values to go with it. So it's just the function value itself and then the first k minus 1 derivatives. So if you know something about how your data is supposed to behave, especially like if you're approximating a given function f of x, and where you know its derivatives at these points, then you can work that into your interpolating polynomial. And you can, oscillatory interpolation allows for a lot of flexibility. You can decide to specify a zillion derivatives at one point and no derivatives at another. It's very freeform. The most extreme case is where you have only one interpolation point, x naught, and you specify the value of f prime, f double prime, and so on, all at x naught. Can anyone tell me what polynomial, what's the name of that polynomial that you get from doing that? You specify everything at one point, because you've seen it before. What? Close, but more generally, Taylor. Yeah, it would be the kind of it's zero. Yeah, it's Taylor polynomial approximation, because that's what it does. The Taylor polynomial approximates f and a certain number of derivatives, all at x naught. So near x naught, you get an excellent approximation, but away from that, not so much. And then if x naught is 0, that's the Maclaurin polynomial. So that's one extreme example of oscillatory interpolation. But what I'm going to talk about here is a different kind called Hermite. That's how it's pronounced. Hermite interpolation, not Hermite. Okay. So in Hermite interpolation, what you do is, here are your x values, just like before, x naught up to xn. You list them twice. So you specify for every single point the function value and its first derivative value. So, so the thing is, now, instead of having n plus 1 points, you effectively have 2n plus 2 points. Now, when you had n plus 1 points, your polynomial was of degree n. With 2n plus 2 points, your polynomial is of degree 1 less than that. So it's degree n plus 2n plus 1. So that's how I'm going to identify my Hermite polynomial, capital H sub 2n plus 1, to indicate the degree. And it's always an odd degree. So here are the conditions that a Hermite interpolating polynomial satisfies. It has to match the function values at all the x's, and that we had that before. The new conditions are the derivatives have to match at those same points. Now, in the textbook, I show how you can represent the Hermite interpolating polynomial using, they're not Lagrange polynomials, but they play a similar role. in that they're equal to 0 at certain points and 1 at certain points, and also their derivatives. I'm not going to discuss that here because it's actually a very cumbersome way to come up with an Hermite polynomial. The easiest way by far to construct a Hermite polynomial is to use Newton form. And I'll get to that in a moment, but first, here's the error formula. It's really is exactly the same as the interpolating polynomial error formula that I showed you earlier, just reflecting the fact that each point is listed twice. So we have, because your interpolating polynomial is degree 2n plus 1, you have the next derivative, 2n plus 2 here, and then you have 2n plus 2 factorial. And because each point is listed twice, all of these factors are squared. That's the only difference. But if you consider the fact that each point is listed twice, it really is exactly the same formula as what we saw before. Okay. So with the Newton form, a couple sections ago, what we did was we constructed a divided difference table, and that's how we got the coefficients of the interpolating polynomial. We're going to do that again, but with each point listed twice. So I have, so what I do is, here is my example. I have two distinct x values, 0 and 1. Now, each one is going to be listed twice, so it's like I have 4 points. That means my Hermite polynomial will have degree 1 less than that and have degree 3. So, so now I'm going to define my z's are my interpolation points with duplicates. So I have only 2 x values, but I have 4 z values. So z0 is 0, z1 is 0, z2 is equal to 1, and z3 is equal to 1. So, so that's how I'm listing each x value twice. And I'm specifying that my function values at both points are equal to 0. My derivatives at both points are equal to 1. So here's another way of describing what I want my Hermite polynomial to satisfy. That at x equals 0, the function is 0, the derivative is 1. And then at x equals 1, same thing. Function value is 0, derivative value is 1. Okay. So now, so here's how I do a divided difference table. I want to emphasize, this is exactly the same divided difference table that we saw with the Newton form. You fill it out in the same way. There's really just one difference, and that is in accounting for the fact that you have certain x values that occur in pairs. So here I list my x values with duplicates. Each one is listed twice, so 0 twice and then 1 twice. Here are my function values. I've just made up data here, so they happen to be 0. And then when I go to the next column in my divided difference table, what would I normally do? I would take this minus this divided by this minus this. But here's the problem. Those values are exactly the same. I'm going to get 0 over 0. So what I do is, in this spot, in a divided difference table, I fill in the derivative. So here I have x equals 0, and then the corresponding y values. So here I fill in the derivative at x equals 0. Down here, I don't have to do anything with derivatives because I have this minus this divided by 1 minus 0. These points are different. So I'm able to compute this divided difference the normal way. Then I go down here. I have identical y values divided by difference of identical x values. So again, I fill in the derivative. So here I fill in the derivative at x equals 1. So what happens is, as you fill in the second column, every other divided difference, you fill in a derivative value from your original data. The divided differences in between, you just compute normally. And once you do that, then you finish off a divided difference table just like you did with the Newton form. So like to get this next column, I do, to get this divided difference, z0, z1, z2, I do this minus this divided by z2 minus z0. Those values are going to be different, so this is going to be well defined. And then same down here, this 1 minus 0 divided by z3 minus z1. Again, they're distinct, so there's no problem. And then finally, this divided difference is going to be this minus this divided by the extreme z value, z3 minus z0. And again, that's well defined. So you go ahead and fill out your divided difference table, taking the derivatives into account in this column, where the first order divided differences are. And once you've done that, like with the Newton form, you read off the top row. So 0, 1, minus 1, 2. Those are your coefficients, and you just pair them with the appropriate linear factors for your centers. So actually, oh good, I can have both of my screen at the same time. Yes, I know, I'm sorry, I'm boring you. Okay, so, sorry I had to. Before I continue, I can't really see because it's a very small screen. Is there anyone in Gulf Park? Okay, 3 people marked absent. Fine. Okay, now, so my coefficients, 0, 1, minus 1, and 2, right off the top row. So I have 0 by itself, and then I have the next value, 1, times x minus 0, because 0 is my first interpolation point. And then I move to the next, and I go minus 1, and then I have my first 2 interpolation points, 0 and 0. So that's why I have x minus 0 and x minus 0. And then I go to my last coefficient, 2, times my first 3 interpolation points in linear factors, x minus 0, x minus 0, x minus 1. So you keep piling on those linear factors. And now you have your polynomial written in Newton form. And then I go ahead and condense it here. So this is my final polynomial. Now, if I really wanted to, I could multiply this out and get it in power form. I just didn't bother to do that here. But I want to show you what this polynomial looks like in MATLAB. So I have, okay. So I have x, I have minus x squared here, and then I have a minus 2x squared here. So I'm really going to have, if I multiply this out, I'm going to have x minus 3x squared plus 2x cubed. So if I do, okay. All right, so I have, well, first I want to have a vector of x values for plotting purposes. And I'm just working on 0 to 1 because that's where my data is. And my polynomial, like I said before, we have 2x cubed minus 3x squared plus x, and then plus 0. There's no constant term, so I have to include that. So now I can get my y's by plugging the x's into that polynomial. And I'll close down my figure windows, and I'll plot this polynomial. Okay, here it is. Okay, now this is not quite to scale as I would like. Actually, that'd be pretty cumbersome to do. Well, I can kind of almost get it to scale. Okay, this is almost to scale. So notice at x equals 0 and x equals 1, the function value is 0. Also at x equals 0 and x equals 1, look at the slope. The slope is 1. And since this graph is almost scale, you can kind of tell the slope is on the screen is almost 1, but it's exactly 1. And those are the only conditions that this polynomial had to satisfy. So what's been done here is to come up with the unique cubic polynomial, which has 4 coefficients, such that we have these function values at the endpoints, and then these same derivative values at the endpoints. And this is what we ended up getting. So if you know something about the slope of your data, you can use Hermite Interpolation to try to match that, and you might be able. So Whereas if I didn't have any derivative information, I had this value being 0, this value being 0, and then the values at a couple points in between specified, I could do regular like Newton interpolation or Lagrange interpolation, but I get a very different function indeed. Okay, so that actually, I think I've come to my last slide. Yes, it is the last slide. Well, have any questions about the process here? So to recap what's going on with polynomial interpolation, that we so if you have certain x values and you want a polynomial to match a certain function at those x values, and also if you have derivative information, you can match that too. So you can either use a approach of using Lagrange polynomials that are equal to 0 or 1, depending on what you need at these points to construct them, and that'll come in handy later when we get into differentiation and integration. But a more practical way has been to use Newton interpolation, where you take your given data, your x values and y values, and complete a divided difference table. So you'll be doing a fair amount of that on homework 3 or working with divided differences. And then you get the polynomial in Newton form, which makes it very easy to update if you need to add additional terms. But then there's also the process of nested multiplication, which you can use to get your polynomial from Newton form into power form. That's much more convenient. And then you can also, and let's not also forget, Horner's method is a method for efficiently evaluating a polynomial that's in power form. That cuts down on the number of multiplications. And the other main point from this chapter is how you choose the x values if you are able to choose them. You might not be able to. In your particular application, you may only have data at certain points, like for instance, temperature given on certain days or something like that, or certain times. And you can't deviate from that. You have to try to fit that data. But if you have a choice, equally spaced points is not good at high degree. Using a Chebyshev points approximates a function much more effectively, and then high degree becomes more practical. Okay, but the main reason for our purposes in this class in covering polynomial interpolation is how we're going to handle derivatives and integrals. If you are approximating a integral or derivative, like a derivative at a point or a definite integral over AB, you approximate the function by a polynomial, interpolating polynomial, and then you can easily integrate or differentiate the polynomial exactly. So these techniques for polynomial interpolation we will use to develop methods for approximating derivatives and integrals, and that's what I'm going to start covering on Tuesday. So what I'm going to do is, I will post these slides along with the MATLAB diary as usual, and in the so when you get to since you're presumably about to finish homework 2, please do not wait too long before getting into homework 3, because that's due just after fall break. The midterm is the Thursday after that, and there will be 3 problems on the midterm that deal with polynomial interpolation using Lagrange form, Newton form, and there's also a Hermite problem. So you want to be well versed in these techniques from doing homework. So don't wait too long, but yeah, you're going to have to scroll back for your notes for what you need. So if there are any questions in the last 2 minutes, or we can call it a day. Yeah, I figured anyway, so okay. Scram. Well, unless you're in this next class, but yeah.